so now let's finish up this chapter. Okay, so here are some fun slides. Okay, this is what is called a velocity selector. Okay, what the diagram shows you is the following. So let's okay, so what this is showing you is so here's a parallel plate capacitor. These brown lines are electric field lines, and the blue crosses are magnetic field lines. So we in this contraption, you have perpendicular electric and magnetic field lines. So here are the electric field lines going from the bottom to the top, and the magnetic field lines into the plane of the paper. Okay. And what this device is if you have a charged particle with the right velocity, so if you throw this positive particle, V cross B will be a force. So V cross B will be a force in the upward direction. Wait a second. V cross B will be a force in the upward direction. Okay, so what you want is electric field. You want, okay. So the magnetic force on this positive charge will be in the upward direction, and now the electric force will be in the opposite direction. Okay. So you see the magnetic force is stronger. So let's make the electric field a little stronger. Not quite. Okay, so you can, as you can see, you can play around with this. Anyway, you guys get the idea. So this is the last try I'm going to give. Almost there. Okay. So with the crossed electric and magnetic fields, particles with only certain velocities will go through straight. Okay. Oh, I can't change the velocity. Horizontal velocity. No, that's what it does. Okay. So particles with a precise velocity will go straight through. Okay. And every other particle will hit this barrier. Okay. So this device is called a velocity selector. So what you do is, so what we're getting ready to do is talk about mass spectrometers. You want to measure the mass of an atom. So imagine this. So you're trying to measure the mass of an atom. The mass of an atom is roughly about 10 to the minus 26 kgs. Your mass is about 100 kgs. Okay, so you're trying to measure something that is 10 to the 28 orders of magnitude lighter. 10 to the 28 is 10,000 trillion times lighter than you. You're trying to weigh that. Okay, so if you want to weigh an atom, you ionize it and then shoot it through a crossed electric and magnetic field. Only atoms, ions of the right mass velocity will get through. Okay. So this is a velocity selector, and atoms of this velocity, velocity equal to E by B, will pass through. Okay. And then what you do is, after you pass them through a velocity selector, now you throw it in, you bring the ions in a region where there's only magnetic field, and the ion will go in a circular path. And you saw that the heavier the particle, the bigger the circle it goes through. So here's the relationship mass divided by the charge. You make sure that you ionize, singly ionize them. Mass divided by the charge is R times the magnetic fields in these regions. B naught is the magnetic field in this region. B is the magnetic field in this region. Okay, so the mass is related to the radius. So you measure the radius of the circular path and you get the mass of the ion. Okay, that's how you weigh atoms. Okay, so that's a mass spectrometer. And we have one of these in the chemistry lab in our department. Okay. All right. So here's the cyclotron I was talking about. So you would apply an AC voltage to this. And if you wanted to accelerate an electron, when the electron comes here, it comes to the edge of this D, you make this positive and it'll accelerate across the gap. And then the magnetic field makes it go in a circle. And when the electron reaches this gap, you make that positive. So that's how you keep accelerating it. Okay. And then eventually the electron is spit out, yeah, at a fast speed. So this was the first type of accelerator. Okay, here's the Hall effect. Okay, so I'll go to the next slide and I'll show you what this is. Okay, so here's a conductor. What this is, we'll understand this diagram. And if you pass a current in this conductor, and what you're doing is you're placing this conductor, so this is a flat slab, and you're placing it in the presence of a magnetic field. So you're passing a current through this conductor in the presence of a magnetic field. So if you have this magnetic field, now if in the conductor the charge carriers are negative, so if you pass a current like this, electrons are flowing in this direction. Because of this magnetic field, they feel a force, and some electrons collect there, and so that becomes positively charged. And there will be a voltage across in the direction perpendicular to the direction of current, and that's called the Hall voltage. Okay. Now, if the charge carriers are positive charges, so this happens in semiconductors, you see this end becomes positive. So if you pass a current in the same direction and the magnetic field is like that, the Hall voltage the polarity of the Hall voltage depends on what kind of charge carrier you have. So if this was a copper slab, the charge carriers are electrons, this end will become positive. And if it's some kind of P-type semiconductor where the carriers are holes, then this end will become negative. Okay, so using this Hall voltage, you can measure the magnetic field. So you can do one of three things. You can measure the magnetic field, you can measure the charge type, what are the charge carriers, and the carrier density. Okay, so this voltage, the Hall voltage, depends on the current, the strength of the magnetic field, times the length of the width of the slab, the carrier density, the charge, and the area of cross section. Okay. So anyway, so by measuring this Hall voltage, you can, if you know all other quantities, you can measure the one unknown. Okay. So that's what Hall voltage is about. Okay. So here's an MRI machine. What you can do is MRI scanners can identify tissue type of a cube that is 0.5 millimeters on each side. So the resolution can be as small as 0.5 millimeter, okay, in an MRI image. And again, the stronger the magnetic field, the better the resolution. So a strong magnetic field in there can make this resolution even better. And they can go through a patient's body point by point and build a 3D map of a tissue. So if you wanted to take a brain MRI, you can make a 3D image of the brain using this technique. Okay. It's a long story, so what I'll do is I'll give you a very, very brief uh, view of it. Okay, so intense magnetic fields are used in MRIs, and again, like 2 to 3 Teslas. They identify tissue types. Okay, and so MRI machines use about 2 Teslas. Fields up to 60 Teslas are possible in research. Okay. I'll let you guys read all of that. MRIs use magnetic moments of protons. Okay. Now your body is full of water. And okay, so your body's okay, so it turns out that so every electron is spinning, and so every electron has so this is an electron, and it has a magnetic moment. By the way, so the magnetic moment of an electron is in the opposite, in that direction, and here is a proton, and a proton is also spinning, and its magnetic moment is pointing in that direction. Okay. Now, it turns out that the electron, the electron magnetic moment is about 2,000 times the proton magnetic moment. Okay. So, really, the electron is a strong magnet compared to the proton, except that in all molecules, in neutral molecules, what happens is every electron, for every electron spin like this, there's an opposite electron spin. So the electron moment cancel out. So in the MRI, you're detecting a weaker magnetic moment, a proton magnetic moment. Okay, again, like I said, I'm going to keep this very brief. The story is long, but so if you have a magnet in the presence of a magnetic field, okay, this is a low energy state, and if the moment is pointing in the opposite direction to the magnetic field, this is a high energy state. Okay, so now let's do just a energy diagram. So this is the high energy state, this is the low energy state. Okay, so if you flip the magnetic moment from a parallel state to an anti-parallel state, you've gone from a low energy state to a high energy state. Okay. So in an MRI machine, what you do is you send in a photon. Okay. You send in a photon and you you excite the moment. That is, when you've gone this way, when you've gone from a low to a high energy state, you flip the magnetic moment. You've gone from here to there. Okay. And when this falls back, that is, this thing goes back from here to there, it'll emit that photon again. Okay. And that's what you detect. So you excited the spin, you took it from low energy to high energy by sending in a pulse, and then you wait for the spin to de-excite, and you're watching these photons, and that's what you're taking the picture from. Okay, now this energy level, so here's the important one fact, this energy difference, delta E, is proportional to the magnetic field. So that's key to understanding this. Now the thing is, so what you want to do is, so let's say So here's the head of a person. Let's say you want to take a picture of this spot. Okay. What you do is you make the magnetic field different at every spot. The magnetic field is different at every spot. So if you want to take a picture of this specific spot, you make sure that you know what the value of the magnetic field is. The energy difference depends on the magnetic field, and only this this location can absorb this photon. This photon has to match this energy difference. Okay, so you send in a photon, only a particular location can absorb that photon, and then you wait for it to excite, and you're watching for that photon to come up. Okay, so that's how you take pictures of different spots. Now you want to take the picture of this spot, you change the magnetic field, and only this spot has the appropriate magnetic field. Okay. So here are the protons in the higher energy state. Here are the protons in the lower energy state. Okay. So you want to take a picture of the head of a person. What you're doing is this is a superconducting magnet. This produces a uniform strong magnetic field, and then there are other magnets that will make sure that there are gradient magnets that will make sure that the magnetic field at every spot in your head is different. Okay, so gradient magnets are turned on and off very rapidly in a specific manner, altering the main magnetic field at a very local level. This allows one to pick exactly which point to take a picture. So you're taking a picture of the intersection of these three planes. So that's how you do this. And so MRIs can apply specific RF pulses using coils targeted at the spot being imaged. Pulses cause photons in the area to absorb energy and jump to a higher level. Okay, so pulses will cause the protons to flip their spin, and what is happening is they're going from a lower energy to higher energy when they absorb the photon. And when they de-excite, they emit a photon, and this is what you're watching for. And you take a picture of that. Okay. So you take a picture of each point. You're taking a picture of the point of these three intersecting points. And then you take pictures of millions of points and then assemble the image, 3D image on your computer. All right, so that's how MRIs work. I know I gave you a 30-second view, but that's the story. Okay, so here's how electric motors work. Let me show you the electric motor. This is very important to understand. What happened? Okay. You guys can look at this. Let's go to my website. All right, I guess we'll have to go this way. Okay, so here's a DC motor. Okay. This step. Okay, right now, okay, the current is flowing like so. So this is the positive charge. Here, the current is flowing like so. Okay, and the current is flowing in this direction. If you hold your fingers along the direction of the current, the magnetic moment is pointing in that direction. Okay, there is the North Pole. Okay. And the magnetic field is pointing in that direction, and you see the magnetic moment is pointing in that direction, it's trying to turn in that direction. Okay. And now the magnetic moment is lined up with the magnetic field. And because of these things, the way these brushes are connected to there, so the magnetic field is pointing like that. The magnetic moment is right now was lined up. The current has gone to zero, and it overshoots. Now this brush touches there, so the current is going from this brush again here like this. It's going in that direction, and now the moment is switched, and the moment is pointing in the opposite direction. And again, it'll turn it and line up with the magnetic field. So the way this is connected, the moment is flipped at the right instant. Okay. So you pass a current through this loop, and it makes in the presence of a magnetic field, and it turns the loop. Okay. And so electrical energy is being converted to mechanical energy, and that's an electric motor. Okay. All right, and like I said, 90% of the work is done by electric motors in the world, so you want to understand those. And again, what does an electric motor do? It converts electrical energy to mechanical energy. All right, so we will